Dear Professor and faculty member, my name is Sukma.meganova FND. I'm a doctoral student in Rajamangala University of Technology, Tanyaburi. I want to present my homework about system identification and simulating for hydraulic simulation. The outcome of this homework is determine test fit transfer function estimation more than 80% for hydraulic servo system simulation using system identification and simulate it in Simulink model. This is the picture of hydraulic servo system. A hydraulic servo system or a plant is a closed-loop control system that use feedback to accurately control a device. A hydraulic servo system consists of a feedback system, a control device, and output sensor. The feedback system uses the output signal and compares with the desired value, and the controller generates the error signal, which are sent to the actuator. This process continues until the output matches the desired value. This is the input, desired value. This is the output, actual value. And then this is the controller in the Laplace. With the symbol is G1 in Laplace domain. And then this is the plan. This is the plan. The symbol is G2 in Laplace domain. And then this is the feedback. The symbol is H in Laplace domain S. This is the input is R in Laplace domain S. And this is the error E. The symbol is E in Laplace domain S, and this is the output is C in Laplace domain is S. The transfer function is a convenient way to represent a linear time invariant system in terms of input output relationship such as a plan. This is the transfer function of G S is equal to output divided by input. The output is Cs and the input is Rs. This is in Laplace domain. The system identification of hydraulic servo system. The system identification is a process that uses measurement of the system's input and output signals to create mathematical models of dynamic system. A model is an abstract and simplified description of system using mathematical equation and diagram. This is the input, output, this is the plan, and this is the model output. Then measurement of the system input and output, and then process until get the best model. The requirements of the process of system identification, there are four. The first is measure the input and output signal from your system in time or frequency domain. And then the second is select the model structure. And then the third is apply an estimation method to estimate value for adjustable parameters in the candidate model structure. And then the last is evaluate the estimated model to see if the model is adequate for your application needs. This is more explanation about the simulink. Simulink is block diagram environment to model a system and then simulate the dynamic behavior of that system. Simulink provides a graphical editor, customizable block libraries, and solvers for modeling and simulating dynamic system. This is the result for the system identification. This is the window of the system identification setting, and this is the figure of the model output. In the system identification, there is some menu for making the import the data and working the data, and also the validation data, and then also we can put the estimation. This is the result of the estimation. We can set until make a fit best fit estimation, and then we can put the best fit estimation into the workspace to process in the command window. And then also we can show the graph of time plot, data spectra, frequency function, and also in here for shown the model output figure, model receipt, transient response, frequency response, zero and false noise spectrum in the figure below. And then this is for the result of estimate transfer function. After we got the best fit estimation, then just double click and then show the window of estimate transfer function. This is the result of estimate transfer function. We can see in the window of estimate transfer function. This is from the menu in here, the menu of estimate. We can write the name, and then after that we can write a value for the pole and zero equation. This is for determine the polynomial of the system order. If in here is 2, so this is the second order. If in here is the value is 3, so it means the third order, and so on. And then after that, after the estimate setting is wrote, and then after write the pole and zero value for estimation, then just click button estimate, and then the result is shown in the window identification progress. We can see in here, this is the iteration, and then we can see in here the fit estimation value in for the pole 202. The fit estimation is around 81.09%. So for this homework is to make the best fit more than 80%. So in this estimation is shown the result is more than 80%. And then after that, this is the result of the transfer function. After in the previous slide in here, after we got the best fit estimation, then just drag the picture to the two workspace in here, and then we can get the name of the best fit estimation, and then we can see in here, this is the 0 and this is the pole. This is like the numerator, or pole is denominator. The pole is the second order, and then the 0 is second order, and also the pole is second order. We can see from here, this is s to the power of 2, or s squared. Then also we can see the fit to estimation data in here. And then this is the picture of the simulating or hydraulic simulation. I can show after this in the MATLAB. This is the result of the simulating. This is the picture that I made in the simulating in MATLAB, and I will show the MATLAB experiment. Just open the MATLAB, and then after that, I write the matrix value for magnitude with the symbol m, variable m, and then the matrix of phase shift with variable p, and then the matrix of frequency with the variable is f. This is the value, all the value of magnitude, phase shift, and frequency. Then after that, save the M file, and then I call the M file in the command window. The name is hydraulic matrix, same with the name of the M file. And then we can see in the workspace, there are like value that's shown in the table, the value of magnitude. You can see here the value is this, and then the value of p in here, and then the value of f. And then after that, we just write ident. This is for open the identification. Or you can use the app and then go to the system identification. It's same way. Then after that, this is the window of system identification. Then go to the import data. Just click in the choose frequency domain data, and then put in here the input, output, and the frequency. The name of the variable of input is M, P, and F. And you can use name. I use this is for 40 bar, and then frequency unit is radian per second, and then the sample time is used 0.005. Don't forget to choose in the FRD amplitude and phase. Change to the FRD amplitude and phase. Okay. Then after that, import. Then we can see in here, this is the picture of the data. Then click the, drag the data to the working data and also to the validation. Then just go to the, here we can see the, and then click in the frequency function, so we can see this is the window of result of the frequency function data. Then after that, we can make the estimation by choosing here for transfer function model. And then we can write the name. I use this is transfer from 0. The first I will put the value of pole and 0 is 1 and 1. Then just click estimation, and we can see in here directly the fit estimation is 53.68%. But in this problem, we have to make the estimation is more than 80%. So in this estimation is not, so in this estimation is, so in this estimation is not shown a good, so in this estimation is shown not a good estimation. And then we can make the estimation again. I change the pole to, I will try the 0 with second order. Then we can see that there is a warning when we estimating the continuous time model using discrete time data. The number of poles, the number of poles must be greater than or equal to the number of 0. So the pole is must be greater than number of 0. So we cannot make like this. We can put the pole with number 2. This is the second order. Then estimate again. And then the result is the fit to estimation data is 80.92. The result is looks like almost good. And also we can see the model output. We can see here, this is the blue one is from the estimation. The pole and 0 is 1 and 1, and then first order, and then the green line, this is for, in the green line, this is for second estimation with the number of pole. This is the second order, and 0 first order. And then I will try for the second. This is for second order for 4 and 0, then estimate again. In the red line, the estimation is better than before, than using the full in second order, the 0, 1, the first order. So I will choose the last estimation with the 4 and 0 is second order. With the estimation is around 81.09%. Then we can see in here from the model output, the graphic, the line is almost similar with the data. And then we can also show the frequency response. Just click in here, frequency response. The picture is like this. And then the transient response is shown like this. And then we can go to the system identification. And then we can go to the Simulink. I already opened and I already made. This is the Simulink that I made. This is the sine wave. We can put the sine wave by double click. Double left click, just double left click on the mouse, and then write the name is sine wave, like this, and then just click, and then the icon will shown in the Simulink window. And the way for put the others icon is same, just double left click on the mouse and then just click transfer function, and then just click again, double left click on mouse, transfer delay, and so on until all the icon is shown, until the icon is complete. And then after that, setting the value inside the block parameter or inside the icon. For the sine wave, just put the sample time with 0.005. You can also change the samples per period, and you can change the amplitude. I just use the default, the amplitude is 1, the sample period is 10. Then click apply and OK. Then after that, for the transfer function, for setting the value is same, double click in the icon, and then there is a numerator coefficient and denominator coefficient. This is the coefficient in the this is the coefficient of 0, and this is the coefficient of whole from the estimation model. So we can see from the system identification window, we can double click the estimation, the picture of the estimation, and then we can see in here from the data or model info window of the estimation, we can see in here, this is the transfer function that used for in the icon transfer function in Simulink. Or we can know the transfer function by drag the picture of the estimation to the workspace. And then we can see in the workspace there is a value of transfer function 2, TF2. And then we can call the information of TF2 by writing TF2. Then we can see in here there is a transfer function, and also there is an information about fit estimation, and then the information of full and zero of the transfer function. Then back to the Simulink again. So we can write the coefficient of numerator or 0, and then write the coefficient of whole from this transfer function. Okay. You can see we can change this one with the value of minus 0.005502, and then space, double space, and then the value is minus 0.0, and then for the coefficient of whole, then just apply, click apply and OK. This is for the icon transfer function and setting the coefficient value of nominator and denominator, and then add transport delay, and then after that add sim out, this is from two workspace, and then this is add the scope for monitor the result in the graphic, and then this is for the sim out one. This is also from the two workspace. I can I will show. This is from two workspace, just like this. And then this is the gain. Just click right gain like this. And then this is sum. This is the constant. Just like this. And then setting the constant with -3 like this. Apply and then OK. And then for this output and input, from this is same from two workspace, and then this is the display, just like this. And then this is also same, this is scope and scope 2, and this is scope this. For the scope, the default is only there is one arrow. So if you want to add the other input for the scope, just drag your mouse in here until there is a plus symbol, and then just left click. Then we can see there is two input in the scope. And then after that, wire all the and then after that wire for all the connection, and then after that wire all the connection like this. Oh, and don't forget in here there is a multiplexing. In here just click moves, and then after that connect, and then after that wire all the connection like this. Then after the block diagram is done, then just run this Simulink. There is a three picture from three scope. Scope 1 is from here, the output of the transport delay. So this is the signal of the transport delay. And then this is the scope. This is from this. Scope is from the input from sine wave and also from the output from transport delay. And then The scope 2 is from summing, is in yellow line, and this is from input and shown in the blue line. So this is the result you can see in the scope 2, scope 1, and scope. This is the result of the estimation. So the conclusion of this estimation for transfer function estimation from second order of 0 and 4, or nominator and denominator, or output and input of transfer function is the transfer function introduces damping and phase shift, which may help stabilize the system, but also reduce the amplitude of the response and introduce a delay. These effects, these effects are generally good if the goal is to stabilize an oscillatory system. If the system aims is to minimize oscillation or prevent instability, then this transfer function does have a good impact. However, if the goal is to match the input more closely, then the damping and phase shift might not represent an ideal fit, and you may need to adjust the transfer function parameter to achieve a closer fit to the desired output. This is all my explanation about this homework. Thank you for watching.